Welcome to Full Momentum and HEC Raz Podcast, episode number 41. I am your host, Ben Carey, and here joining me, as always, my partner in crime, Chris Goodell. Chris, welcome to episode 41. It's been about a month and a half since we did an episode, but we've had a busy summer thus far, and as we move into fall here, I know we got a lot of exciting things going on. So how are you doing today?
Pretty good. Yeah, we had to let it kind of sit on that 40th episode for a while. That was a bit of a milestone for us. But yeah, we got a lot going on. You and I are both moving into new houses. How about that? At the same time. Not the same house, though. Although it'd make podcasting easier, maybe.
Yeah, we could do in-person podcast a little bit simpler if that was the case. But yeah, both of us kind of making some changes on the house front, which I know has taken up quite a bit of time in our free time at least. And then we also have a lot of changes going on. Good changes within our professional career as well. So one of the exciting opportunities that we were looking forward to sharing with everybody on today's episode is, for the first time, I think in like 4 years, Chris and I, our group at Kleinschmidt, our H&H group, has an open H&H posting that just went up this Friday, September 5th. And we're looking to hire a E2, E3, which is kind of more closer on that entry level scale of things. So we're looking for somebody to come in and work with us on a lot of different cool H&H related projects. We're going to certainly want to involve you all in a lot of RAS modeling, but there's also some opportunities to grow into some CFD modeling, some hydrologic analysis. Part of our team does quite a bit of work on the restoration and hydraulic design side of things. So it's a really cool opportunity for folks that might be interested in working with us. And like I said, it's been a while since we've had one of these postings up. So Chris, I don't know if you have any additional thoughts you want to share with everybody.
Well, I imagine there'll be lots of opportunity to get out into the field too, which is attracted to a lot of younger engineers, especially. So if you like getting out in the water, into the rivers, and going on some really cool hikes to do some work out in the field, this is a good opportunity for you. But there'll be a lot of opportunity to do some modeling work as well. As you know, Ben and I do a lot of HEC-RAS modeling. We also have folks in our section that do a lot of CFD modeling. So lots of opportunities. This will be a really fun position. Ben, what do you look for in a new hire?
Yeah, obviously it depends on the level that we're hiring for, but for this position, I think the biggest thing that Chris and I always look for, especially when it comes to interviews, is just a real interest and energy around learning, right? We're not naive enough to think that anybody who's going to be hired at this level is going to come in day one and know exactly how to do all these different projects and analyses. But what we do want to see is somebody who's really interested in learning and has a lot of energy around that. I think that has been really successful for us in the past in terms of finding good people and building out the H&H team. And so that's the biggest thing for me. Obviously, if you have experience in some of the software that we're going to be using, that's a bonus. But really just somebody that's interested and has a lot of energy. Also would be a huge benefit if you're located near one of our company offices and can prioritize coming into the office and seeing people a few times a week. That's another thing that's not required, but certainly something that we're strongly considering, because again, we've had a lot of success within our H&H team having quite a bit of in-person touch points, which has been great. And Chris, I'm glad you brought up the idea of field work, because that is something certainly that our junior staff are asked to assist a lot on. For those that aren't aware, Kleinschmidt is a very multidisciplinary company. We have scientists and relicensing, engineering of all different types. And because of that broad spectrum of work, there's a lot of different field opportunities where sometimes, our science or regulatory or engineering teams get a little bit busy and we need to fill in. And so there's some really cool opportunities that I personally got to take advantage of when I was a little bit more junior. And I know that a lot of the folks on our team, some of which that have actually shown up on the podcast, and I know Robert's been on the podcast, Isha, Rowan, these people have all had a chance to get out in the field too, and I think really enjoyed that part of it as well. Uh, so the actual advertisement I'm sharing the screen here. If you go to kleinschmidtgroup.com, we'll include a link to this posting. And you go to our open positions page, you'll see this H&H staff engineering position. You can see it's listed as the Portland, Oregon or the Portland, Maine office, but we're open to other locations depending on where the talent is at. And yeah, looking to fill this position as soon as we can. We have a ton of work that's ongoing as well as coming up in the near term, and we're needing some assistance with that. So again, if you're at all interested, I'd strongly encourage you to throw your resume out there, or reach out to Chris and I. Maybe leave a comment on this video, and we can engage with you and maybe answer any questions that you might have. But a really cool opportunity for those that are coming out of school, or maybe just looking for a change in terms of what they're currently doing. So
Yeah,
really
yeah, what I look for is kind of on the same lines as what you're saying about learning, but I like to see somebody who has a passion for what we want to do, somebody who really wants to get into this industry. We're a hydropower firm, but we get into restoration work, and we do a lot of work around rivers and reservoirs and streams and even some coastal stuff. And if that's your interest, if you have a passion for that kind of work, for modeling, hydraulic modeling, that's the kind of people we want. And yeah, you don't have to know everything. We have people here who can teach you, but what you can be taught is to have a passion and interest, an enthusiasm for this kind of work. And so that's what we really are trying to find.
Yep. Absolutely. Cool. So that's one opportunity. The other thing that I wanted to mention, which is really exciting, is the next training opportunity that's going to be available to anybody out there that's listening. So Chris and I have already done a number of classes this year. Chris, you're actually getting ready to head out tomorrow, on the 6th of
I
September.
am.
Fly out internationally to teach one of these classes to our friends in Norway. I know that's something that you get a chance to do every year. And so if you are interested in registering for our next upcoming class, well, good news, our class starts in about a month. So we're for the first time ever, we're actually splitting up our standard HEC RAS 1D 2D class into two separate classes. And this is just because there was so much content and so much interest in all the different facets of HEC RAS that we just had a really hard time fitting it into 6 weeks. So we felt like it would be better for us to split up this into two classes, be able to really dedicate 6 weeks introducing the fundamentals of HEC RAS 1D 2D modeling to folks that are a little bit newer to the software, and then be able to spend another 6 weeks with folks that are proficient in HEC RAS 1D and maybe have a little bit of 2D experience, but really want to dive into the 2D advanced topics in depth. There's so much cool new stuff coming out with 2D RAS. That includes obviously the new RAS 2025 software release, which is going to be part of that training program. So we have these two kind of alternating classes that we're going to offer. And the first is our fundamentals of HEC RAS 1D 2D class. That's going to start October 1st, so just a few weeks away. It's going to run for 6 weeks from the 1st of October to the 4th of November. And yeah, it's going to be specifically catered to folks that are new to HEC RAS or maybe have a little bit of 1D experience but haven't touched 2D. That's going to be kind of our target audience for this. Obviously, if you're interested in just kind of reminding yourself some of the fundamental concepts and theory around building 1D and 2D models, this is going to be the perfect class for you. And then the way we've designed it is it's going to lead right into the advanced 2D RAS. So there's not going to be much crossover between those two classes at all. So if after that first class you are really enthusiastic and wanting to continue your adventure in learning HEC RAS and want to learn more about 2D, then there'll be an opportunity to enroll in that advanced 2D RAS class, which will be starting in the spring of 2026. I believe we have it slated for March. So really excited to offer this new 2-part series and hopefully open up a whole new group of people that might be able to benefit from taking this training.
Yeah, Ben and I have been working really hard putting together this fundamentals class. It's no small effort, and we're really excited to show you what we put together. A lot of cool content, a lot of really good, valuable content. And this is really going to give you not just the the theory behind it and that kind of thing, but you're going to get practical experience using the software, and that's a really important part of learning is getting into it and doing the work yourself. And Ben and I will be here to help you troubleshoot through those workshops, as well as teach you all the cool new material that we've got here for you.
Yeah.
So yeah, hope to see you there. This will be a fun class.
Absolutely. Yeah. And so if you're interested, again, we'll include a link to the training in this video, or you can go to raztraining.com, click on courses, and sign up for that fundamentals of HTC RAS 1D 2D class. Again, starts October 1st. Highly recommend you get enrolled as soon as possible, just in case that class starts to fill up. We've had that happen in the past where we kind of have to cut things off, and we prefer not to do that, especially because we're not sure exactly when the next offering of this fundamentals class is going to be, because we're going to be teaching that advanced class in the spring of 2026. Okay, those are the
Yeah.
two announcements that I wanted to get into today. Chris, let's get into the technical discussion, which is hopefully why most people are here. So I think we're on a run of like 3 or 4 straight episodes where we've had a guest on and we've kind of talked about a special topic related to that person
Yeah.
and their expertise, which has been fantastic. We had some really, really cool conversations around rain on grid modeling and the use of geospatial satellite data with Ryan Troy. We had a really good conversation with our coworker Paul Drew on dam breach analysis and some kind of do's and don'ts and tricks of the trade there. So we're going to get transition back to our foundation here of how the channel got started, and that is just to kind of take a deeper dive on a specialized topic that maybe doesn't get discussed very much in the industry at large. So I'll let you introduce what the topic for today is all about.
Yeah, and this will not be a fundamental topic. So this is something that's probably more in line with what we would have in our advanced class. But we're going to talk about turbulence today. And I am glad that we are kind of going back to our roots here a little bit, Ben, and gives us an opportunity to nerd out over something together, which we haven't done in quite some time. But I want to get into turbulence because there's a lot of misconceptions out there about what it is in RAS and maybe even more importantly, when do you use it and why would you use it in a HEC-RAS model? So let me get the PowerPoint up here. I've got some slides I want to show. Some of this I actually presented at the Pub and Grub in Atlanta that Ben and I did. Was that last year, Ben?
Yep,
2024? I guess it was. Yeah.
sounds right.
Boy, time flies. So what exactly is turbulence in HEC-RAS? Now, you think of the word turbulence and you think of kind of chaotic motion of a fluid, right? We've all seen very turbulent water. Maybe it's downstream of a spillway, or you're out in a really dynamic river, maybe a whitewater river, a lot of turbulence there. But what is it in the context of HEC-RAS modeling? Well, first of all, the turbulence model that's inside of HEC-RAS does not actually simulate turbulence. It simulates the effect of turbulence, and more specifically, the momentum diffusion effect of turbulence. So how does turbulence affect the diffusion of water as it moves through the system? So what it really does is it simulates the transfer of momentum from areas where you have high gradients, high velocity gradients, to areas of low velocity gradients. And this transfer of momentum is caused by turbulent eddies at scales smaller than the grid. So because these turbulent eddies, I call them micro eddies, right? They're smaller than the grid or the mesh that you've set up. So they're not going to be picked up in the computations, but they do account for momentum change and ultimately energy loss. And so it's something that we want to account for in certain circumstances. So we'll get more into that in a little bit. But one way to think about how this turbulence is handled in RAS is to think of it in the same lines as viscosity and what viscosity would do to a fluid. And in fact, that's the analog that's used to account for the diffusion effects of turbulence, is to treat it as if it were a more viscous fluid. Okay, and that's why sometimes you see the term eddy viscosity out there. It has nothing to do with the viscosity of the water. It does have to do with eddies or turbulence. Turbulent viscosity might be another term you could use, but it's just kind of a surrogate to use, a convenient surrogate to measure the effects of turbulence inside of a hydraulic model. So here's the equation. What RAS does is it actually computes this eddy viscosity coefficient, this kind of V sub T value, and it's based on two types of turbulence. You've got longitudinal and transversal turbulence created from the bed of the river, which is on the left-hand side, and then you got turbulent effects from the edges of the river. Okay, so let's get into this a little bit more. Ben, what do you got?
Yeah, so I thought that was a really interesting point you made around like kind of that's a surrogate for viscosity, right? And I think everybody, even if you're not a, you know, don't have a deep hydraulics background, can appreciate the difference in how water actually can feel as you're moving through it, depending on how much turbulence there is in the water, right? So if you're
Mhm.
swimming through just a flat, unmoving swimming pool, right, that has a consistent viscosity to it, right? And it feels very smooth. There's not kind of that disruption. Versus if you're floating down a river and you go through some rapids and you start to feel some of that turbulence, and particularly if you try to kind of swim through some of those, it can almost feel as though the water has a different viscosity than a slow moving, normal moving water body would have. So that's a really interesting
Yeah.
analogy that you gave. And I think again, if you can just kind of picture swimming through a body of water like this, there would be times in which you'd almost feel as though you're not swimming through just normal water. So that's a cool idea and a way to think about how this additional loss of energy in the system needs to be potentially accounted for, especially again as we're the importance of evaluating the results in a near field setting become highlighted.
Yeah, yeah. Another way to look at it too is if imagine you've got a jet of water shooting into a flume or a canal or something like that, right? And water's pretty low viscosity, but what's a really high viscosity fluid? Oil,
Mm-hmm.
right? Molasses, something like that. Imagine shooting a jet of molasses into a canal or oil. It's going to spread out and even out much quicker, right, than water would. Water would kind of hold its concentration of flow longer than oil would. Oil would spread out and become more uniform much quicker. And that's what you get with turbulence as well. So that's why viscosity is a really nice surrogate to turbulence in the world of hydraulic computations. So imagine this kind of turbulent river that you see right here, and we've got a mesh on top of it so that we can model it. Okay, and this might be, I don't know, 5 foot grid size, whatever, it doesn't matter. But what you can clearly see with this mesh is you've got these micro eddies, you got micro turbulence within the individual cells that RAS can't pick up on, right? RAS does momentum computations over the cell faces. Well, things that happen in the middle of the cell is not going to be picked up on, but that certainly is going to cause some momentum exchange and energy loss, even though it's not necessarily picked up on the cell faces. Okay, and so what's the result of that? Well, when you have a lot of turbulence or a lot of viscosity, higher viscosity, it will take the areas of higher concentration of flow or higher velocities and it'll smooth it out like this, right? The peaks become a little bit lower and the low velocities on the edges pick up, and then ultimately it might become extremely uniform all the way across. Right. And so that's the effect of turbulence that you get.
Now, Chris,
No,
you've said a few times about this idea of this micro turbulence that occurs inside of our individual cells, and RAS doesn't have the ability to kind of capture that, given the
yeah.
fact that the computations take place at the individual cell phases when it comes to velocity and whatnot. Would there be a point at which you make your cells so refined, your mesh so refined that you would be able to pick up and account for these micro turbulences? I guess my question is, do these effects become less important to capture the smaller your cells are?
That is a great question. And yes, in theory, yeah, if you could make these cells infinitely small, you'd be able to see all of the turbulent patterns in here in theory. Now, of course, we're using a 2D model, right? And a lot of this turbulence that you see in here is 3D in nature,
Great
right?
point. Yeah.
So you would never be able to pick that up in the HEC-RAS model, but you can account for it with the turbulence model.
Yep.
So yeah, in a way, yes, you're correct. You would pick up more and more of these micro eddies and these smaller patterns, but you're not going to get it exactly right because of the
Yeah. Then
3D effects.
the reason I bring that up is because I think that idea that you just explained really well is something that trips people up all the time with RAS modeling, which is if I make my mesh smaller and smaller and smaller and smaller, the model will be better and better and better and better. And because of the fact that we're using two-dimensional RAS modeling, right, we're inherently not going to be accounting for any three-dimensional hydraulics. And
Hmm.
so there's a simplification, there's an assumption built into this. And we can kind of sometimes, I think, as users trick ourselves when we make our mesh very, very small in order to make our model better. And it kind of, again, gives you a false sense of security when in reality, you're then ignoring one of the really important premises of two-dimensional modeling, which is that depth averaged kind of process. So just, I guess, a high level takeaway from this, aside from turbulence, but just in general, just remember that this is not a three-dimensional model. And so if there's going to be three-dimensional impacts, you're going to have to account for that some other way. And that
Hmm.
may be with a different model, or
Yeah.
it might be with one of these parameters which tries to kind of capture some of those three-dimensional effects with a single coefficient that certainly has a lot of uncertainty.
Yeah, exactly right. So here's another effect of turbulence. So imagine you've got this river right here, and it's in a fairly narrow canyon, and then it opens up into a larger body of water. We've all seen this, right? This concentration of flow that persists for some time before it spreads out into the big body of water, right? And so I just kind of eyeballed what looks like the diffusion going on here as it enters the bigger body of water before it turns to the right and goes downstream. But how do we know that that's actually what's going to happen? I mean, we could see that here in this example for sure, but if we were to model this, how would we know that this is the correct amount of diffusion? Well, we don't unless we can calibrate. But the turbulence model built into RAS is a knob to turn to affect the rate of diffusion of this jet. Maybe we want it to look more like the orange line instead of the red. Well, we can do that by increasing the turbulent effects, increasing the turbulent coefficients in RAS, and that's going to cause it to diffuse faster. So if let's say you've been out here to this river or this body of water, and you've measured this, you've got maybe aerial imagery like this where you can clearly see the rate of diffusion, and then you go and model it and it looks more like the orange line in your model. Well, then maybe you have to dial back the turbulence a little bit to keep it from diffusing too fast.
Yeah.
Okay, so this is an effect that you'll get by adding or decreasing turbulence inside of HEC-RAS.
Chris, another question that I think a lot of people have when it comes to turbulence is how do you balance and prioritize turbulence and Manning's roughness, right? These are
Hmm.
both coefficients that help, reduce energy within the system. They both kind of account for similar type of physical things in the riverine environment. Um, and you can they both have a lot of uncertainties. You can play with both of them to try to get these calibration results to match better potentially. So when somebody
Yeah.
asks you that question, how do you approach kind of prioritizing Manning's turbulence, which one you adjust, which one you don't, that sort of a
Yeah.
question.
Well, first of all, you have to decide, are you going to use turbulence in the first place in your model? But let's make the assumption that you are. You've got turbulence included in your model. You always have Manning's N in your model. That's a requirement. So my take is, in most cases, most models I've worked on, your Manning's roughness is going to be, or your results will be much more sensitive to your Manning's roughness than to turbulence. And so I always start with Manning's N as kind of my first level of calibration. And then I think of turbulence as a way to fine tune,
Okay.
but also to affect the velocity, or sorry, the flow patterns.
Yeah.
Now, your N values will have some effect on flow patterns, but your turbulence will have a maybe even a more significant effect on your flow patterns. So I guess it's, what are you trying to calibrate? Are you trying to
Yep.
calibrate flow patterns or water surface elevations?
Yep.
I think N values are going to affect water surface elevations more. Turbulence is going to affect flow patterns more.
Yeah. So, and to use this picture, because this is such a good picture to kind of highlight this, right? You might have a model that is either using turbulence or not using turbulence, and you might actually produce the same or very, very similar water surface elevations. But if you looked at the particle tracing output in RAS Mapper, you might actually see different or very different results of the flow patterns and these eddies and how quickly this water diffuses between those
Hmm.
red and orange lines, right? And so
Yeah.
I think it's a really interesting concept that I hadn't honestly thought about, which is maybe prioritizing Mannings to help calibrate to water surface elevations, and then maybe using turbulence to help calibrate to flow patterns, visual representations of how water is actually diffusing it within the system. I think that's a good approach.
Yeah, and I'm going to show you some examples of that here too coming up. So
Cool.
good point. Good point. So okay, we gotta talk about the math a little bit, and the scary squiggly D's, the differentials. But these are the velocity gradients I was talking about, right? And don't be too intimidated by this. Is all this means is change in velocity with respect to distance, right? So the U is the x direction velocity, and or sorry, this is V. V is the x direction velocity, and over here is U, which is your x direction velocity. V is your y direction velocity. And then, of course, you've got x and y directions, right? So this would be the change in your y direction velocity in the y direction. Okay, so it's an acceleration, a spatial acceleration, right? Here we got the change in your y direction velocity with respect to the x direction. Okay, again, a spatial acceleration. Okay, we got change in x direction velocity with respect to y and change in x direction velocity with respect to x. These are the gradients that are considered when modeling turbulence, which in a way kind of makes sense because you've got in turbulent flow, you got water moving in all directions, right? And the rate of diffusion is proportional to the velocity gradients. And so this is how we measure velocity gradients.
Chris, is it reasonable to say that because of that figure that you just had there, it shows obviously the computation points occurring kind of at, the corner of those cells. Uh, in a system where you potentially have, um, you know, differing velocity patterns in a small area, it's going to be important to have a mesh resolution refined enough to be able to have these individual computations such that these acceleration terms that you're describing are computed correctly.
Yeah, I mean, that kind of gets to the basis of building a 2D model, right? Is you want to be able to have cells small enough that you're able to pick up these differences. One thing we talk about a lot is how many cells do you need to have across a conveyance zone to properly model the velocity distribution? And we always suggest to have at least five, but the more kind of the better, really, as long as it's practical. But when you start getting less than that, you're not going to be picking up on these changes in velocity across the channel and the distribution of velocity across the channel. And ultimately, that affects the computed water surface elevation as well. So, yeah, it's a good point. It's important to have enough resolution. But as we all know, too, you make your cells smaller, it makes your models take longer to run. And so there's this balance that you're trying to strike, between accuracy and model efficiency all the time. So here's this is also what I'm going to show you in just a little bit, but these kind of flume demonstrations I did to test out turbulence and show how changes in your turbulent parameters affect the results and whether or not you use turbulence or not. But we'll get to that in a second. So I mentioned before that RAS considers two types of turbulence: turbulence from the bed, both in the longitudinal and the transverse direction, and turbulence from the edge, the boundaries of your model. Okay. So over here we have a longitudinal and transverse mixing coefficient, that's the capital D, multiplied by the shear velocity times the depth of water. Okay, and each direction you have a different diffusion coefficient for longitudinal versus transversal. And there's recommendations in the manuals of what values to use here for different types of turbulence. I'll show you that in just a little bit. We also have the right-hand side, which is the Smagorinsky part of the equation. And there's a coefficient. The manual also provides guidance on what to use for this C sub S value. And then you've got this local grid resolution, delta. Okay, this is basically just the size of your grid. And then the strain rate, which is capital S. Notice here we've got our velocity gradients worked into the calculation of strain rate, right? But when we get into the full momentum equation, which I think we've shown on this podcast probably several times already, but we talk a lot about this in the class. You got your acceleration terms over here on the left-hand side, and you've got your force terms on the right-hand side, and one of the force terms is turbulence. That's this big one right here in the middle. All of this is your turbulence. You got both this equation, both for the X direction and for the Y direction. Okay, notice inside of the momentum equation, you've also got your hydraulic gradients present. Okay, so we're talking like second order partial differential equation stuff going on here, which gets really crazy with the math. But that's how it's done. And there's your eddy viscosity coefficient for the X direction and the Y direction, both present in both forms of the momentum equation.
Yeah, and I just want to point something out here as we show, the full shallow water equations on the screen. And we just on the previous slide, you showed kind of where to input the turbulence parameters, right, in the computation options and tolerances window. And this is something, again, very common misconception, which is if you elect to use the full shallow water equations, your model will automatically account for turbulence or use turbulence. And that's not correct. That's actually a secondary thing you have to go in and establish within the computation options and tolerances window. So
yeah,
there are a lot of people out there that are using the SWE equation set assuming the turbulence is being used and it's not. So that's a really, really important distinction. I wish there was a way that I wish there was an equation set that required you to put those mixing coefficients in, or it would give you some sort of notification that you haven't established those yet. I think that would be probably useful to do.
Yeah, but by default, it's set to none. It doesn't use it. So to your point, Ben, yeah, you have to go in here and you have to turn it on. So you have to hit this drop-down box and select either the conservative or non-conservative turbulence model. Those are the two options you have. But the other thing that's important too is you have to use one of the SWE options, ELM or EM. I don't even think, I could be wrong, but I don't think LIA does turbulence. I might be wrong there, but certainly you can't use diffusion wave with turbulence. Turbulence will not be used in diffusion wave. It's not part of that equation. So you have to switch to SWE and then make sure you turn it on.
You can use turbulence when you're using LIA. Just confirm.
Oh, you can. Yeah. Okay. Thanks for checking on that. Would you just look that up or something, or
I just had RAS
into Chat GPT?
I always have a RAS window open. It's like I always have an empty coffee mug on my desk and I have RAS open. Those are like the two consistencies that you can always count on.
Okay, and so here are the coefficients that you have to enter into the model. So these are provided in the 2D hydraulic or 2D user's manual, HEC-RAS user's manual. And you can see it's broken up into longitudinal as well as transverse mixing. So here we've got our DL values, 0.1 to 0.3 for little longitudinal mixing, all the way up to 1 to 3 for strong longitudinal mixing. And same thing for the transversal. Notice the transversal mixing is a little bit less, which is interesting, and we'll see the effect of that here coming up. There's also the Smagorinsky coefficient. That's the second half of the viscosity coefficient equation, and it gives you nothing more than typically ranges from 0.05 to 0.2. So all this being said, there's a lot of uncertainty in what values to use. If you've got data to calibrate to, whether it's water surface elevations or even looking at aerial imagery of flow patterns. If you can see that with aerial imagery, or you can go out to the field and measure it, um, that's great. And even better is if you can get a velocity distribution across a channel. Like if you use a probe and move it across and see how the velocity changes, you use that for calibration with turbulence as well. Outside of that, then you're pretty much stuck with doing sensitivity analysis. All right, so that's all great, but when do you want to use turbulence in RAS? So that's probably the most important question. Like, hey, I built this RAS model. Should I be using turbulence here? We don't use it all that much on our projects. Maybe we should think about it a little bit more. I don't know. But if you haven't gotten this Project 15 manual from the Australian Rainfall Runoff Project, or yeah, the ARR Project 15, this is a great manual for 2D modeling. I highly recommend it. And if you thumb through there, you'll find a little description or a little section on the what's called the Abbott number. And the Abbott number is a really simple equation. It's just the water depth H divided by the grid spacing, the cell sizes effectively. But why this is important in turbulence is because what happens when your depth gets really deep relative to the size of your cells is you get less of an effect of the roughness, the Manning's number on diffusion. So without turbulence in your model, you'll still simulate diffusion. And that diffusion takes place because of the roughness in the system, the roughness in your model. Well, when you have really deep and narrow cells, that relative roughness has less of an impact and you actually can underestimate the true diffusion. And so a way to capture that or recover that is by turning turbulence on. So it's important to look at your Abbott numbers in your model. If your Abbott number is much less than 1, then eddy viscosity is probably not very important. And friction is going to be the dominant form in determining flow distributions and diffusion. Okay, when you start approaching an Abbott number of 1, in other words, your depth of water is on the same order of magnitude as the grid cell spacing, then eddy viscosity becomes increasingly important. And you might think about turning on turbulence. When your Abbott number is much greater than 1, you should definitely at least test turbulence and see if it makes a difference.
Yeah, that's a really interesting concept. Again, something that trips people up, right, is using the consequences, I guess, of using smaller cells in your 2D mesh, and the idea that as your cells get smaller and smaller, the importance of including diffusion increase is not something I think that's common knowledge out there. And I think really you think about the reason why people select using a more refined mesh is typically because they want more detailed results. They're doing some, analysis around a particular object or through a bridge opening, or as it pertains to, the passage of fish through a complicated series of falls, like those types of questions where you really want detailed, accurate results near field, and yet you might not be using one of the more important parameters in the equation when you have those really, really small refined meshes. So
Yeah.
really, really, really cool.
And I think there's a lot of misconception out there too that, hey, our river needs to look like that picture at the beginning of the slide. This one, before we should think about turning on turbulence. That is not the case at all. Yeah, this is a very turbulent looking river, but I have a little secret for everybody. All rivers are turbulent, whether they look like it or not. If you're basing turbulence on the classical definition by Reynolds number, pretty much all rivers are turbulent. There might be some slight exceptions to that, but they're pretty much all turbulent. So the question is, when does turbulence become an important contributor to the overall energy loss and momentum exchange in your system? That's where you need to include it in the model. Okay, and as I mentioned in the previous slide, the numerical scheme in HEC-RAS without turbulence turned on already provides some inherent numerical diffusion. Okay, and that's because of the roughness that's built into it. But the smaller the computational size and time step, the less numerical diffusion you're going to get. And that's when you might want to think about turning on turbulence to recover some of that. Okay, an Abbott number is a great way to test that, to check and see if you're in that range where you should start thinking about including turbulence. Okay, another reason is if your model calibrates very well to in-channel flows, but as soon as the water gets out of the channel and starts spilling into the floodplain, the overbank, you're having a tough time calibrating anymore. A lot of that could be because you're not including turbulence in your model. Or another way to look at it is a way to better calibrate in that situation is by turning on turbulence. Of course, you can also play around with N values there and maybe get the same effect, but turbulence is there as another knob to turn. All right, so I wanted to kind of get a feel for how all these coefficients and different cell sizes will affect the diffusion rate in a simple flume. So I built this flume model. This is just a rectangular flume. I think it's something like 1,000 feet long, roughly, maybe 100 feet wide, something like that. And I looked at grid cells of 10 meters, 2 meters, and 0.5 meters so that I could compare different Abbott numbers. And the Abbott numbers that resulted from this were 0.26. Okay, that's much less than 1. So in theory, turning on turbulence is probably not going to be necessary here. Then this one's close to 1 where you should start thinking about turbulence. And this is much greater than 1 where turbulence should be considered in your model. Okay, I also inserted a solid wall right here. Just a terrain modification, just a solid wall that forces all the flow to squeeze through this opening on the side. And that's going to set up an eddy pattern right here. Okay, as the water spreads out and diffuses. Okay, you get this eddy pattern. And you'll see with different coefficients or turning turbulence on or not, you're going to see differences in the size of this eddy pattern, which is another way to look at the rate of diffusion in here. And so I consider these different coefficients. These kind of span the range of values that are recommended by the manual. So basically what I wanted to find out here is how is diffusion affected by the turbulence coefficients. So here you can see we're modeling the flume first with no turbulence. So turbulence is not turned on here. And then we're looking at the smaller side of the range of values in those tables all the way up to the largest size. So I'm doing kind of a spread of these values equivalently. So DL, DT, and CS, your Smagorinsky coefficient. And what you can see is this eddy pattern shows up downstream of the wall. So everything converges, squeezes through this opening on the side. Velocities pick up. You can see this higher velocity zone here. And then it starts to decrease as the water spreads back out. And you've got this eddy pattern. Now, what I measured here to kind of figure out the rate of diffusion is where does that eddy pattern extend down towards? So where does that water split? Where on this side of the red line, it's going back up into the eddy. On this side, it's continuing downstream. So that's what this red tick mark represents. And so you can see as we increase or we add turbulence and increase it, we get a smaller and smaller eddy. And so a faster rate of diffusion, right? But not by a lot. I mean, it's not a huge difference. And in fact, just going turbulence to turning on turbulence with the smaller coefficients, hardly see a difference at all. In fact, that difference might just be my own imagination as I drew the tick mark. So not a lot, but notice what the Abbott number is. Abbott number is pretty low, 0.26, 10-meter cells. So what about 2-meter cells? Now you can start to see some more significant difference, especially at the higher coefficients. Okay, when we have 0.5 meter cells, Abbott number is much greater than 1. You can see even more difference. Now, if you focus in on the no turbulence, the one on the left, as I flip through the different cell sizes. Oops, I was going the wrong way here. Okay, notice no turbulence. It diffuses down to about station 445, maybe. Okay. When I just by changing the cell size, not turning on diffusion or not turning on turbulence, notice it jumps all the way down here. Okay. We're getting less diffusion with just decreasing the cell size. And then when I go to 0.5, even less diffusion. Okay, so that's important to note. How do you recover that? If this is the real answer, this is what it should be, but you want to use a cell size of a half a meter, okay, you're going to have to somehow push that diffusion back up here to 445. And you can do that by increasing or turning on turbulence and using relatively high coefficients. Okay, and then the next set of slides just compare the individual coefficients. So in this example, I left DL and DT off, and I just changed my Smagorinsky coefficient. Not a whole lot of change there, right? Okay, so this particular example, not sensitive to the Smagorinsky coefficient. Okay, here I've changed on this again is no turbulence, the first one, and then this second and third one represent a change in longitudinal diffusion coefficient from the low end 0.3 to the high end of 3. Makes quite a bit of difference. Okay, but then when you look at your transversal coefficient, not quite as much of a difference. So this example is most sensitive to your longitudinal diffusion coefficient. I'm not saying that's going to be the case for every project out there, but in this particular flume example, that's definitely the case.
So Chris, let's dive into that. So the longitudinal coefficient is the most impactful in this flume example. Is that in part because it's a flume and you don't have a lot of the, I guess, edge effects that a complex river might have, where you're going to have more transverse mixing, or like what situation would you expect that to be flip-flopped, I
Well,
guess?
I think the primary flow is moving in the longitudinal direction. I think that's the biggest part of it. Now, if you had flow spreading out in all directions, then maybe your transversal is going to be a bigger impact. But I think it really boils down to primarily water's moving in the longitudinal direction in this example. And so it makes sense. But then the other thing too is notice the coefficients are a little bit higher for longitudinal than they are for transversal. So that plays a part in it as well.
Sure. Okay. Yeah, that's interesting.
Yeah. So now here's what I found most interesting. I mean, these are really cool looking plots, and it was fun to play around with this. But from a practical standpoint, look at the differences in water surface elevation between having no turbulence and having turbulence turned on with the highest coefficient settings recommended by RAS. We're talking about less than 100th of a foot difference at the high end upstream of this constriction. So this is just upstream of the wall that I put in there. Here's passing through the constricted section, and then this is downstream of the wall.
Okay. This is with 10 meter cells. Was that 10, the same? Was that the same with 2.5 meter?
Yeah, not a whole lot of difference. I mean, there's a little bit more of a spread with the smaller cells, but I mean, we're still talking less than 100th of a foot difference.
Okay.
So the takeaway for me here is if your objective is really just to get water surface elevations from your model, maybe it's a flood study, you want to see amount of rise upstream by putting in a bridge or something like that, turbulence is probably not going to be a big player in your results. It's going to be more about N values. And you can test it out on yours, and I highly recommend you doing it, especially if your Abbott numbers are high, or there's a lot of contraction and expansion in your particular model. I highly encourage you to test it, but I bet you're not going to see a big difference in water surface elevation. I mean, look at this. This is less than 100th of a foot, maybe up to 5,000ths of a foot difference at the high end here. So yeah, take that for what it's worth. But where you do see the differences in velocity patterns and velocity distributions. And notice here at the most constricted part of the constriction, here's the wall right here. Here's flow coming off of it, constricts down to this point. I looked at no turbulence and with turbulence turned on at different coefficient rates. And you can see what it does to the velocity distribution on that line. With no turbulence, you have this light blue line here. That's the steepest line here. It's the most concentrated flow. But once you start introducing turbulence and you increase these coefficients, you can see that velocity distribution tends to spread out and it distributes it more uniformly, or at least goes that direction. You still have a concentration of high flow here, but it's not as concentrated. It starts to spread out more. Notice that the very narrow bands of color right here, that indicates a really steep change or really high velocity gradient. Here, the velocity gradients are lower once we introduce turbulence.
I guess one other interesting maybe follow-up test that you could have done, and I would be interested in seeing the results, would be maintain the cell size, but change the slope of the flume. Because right
Mm-hmm.
now, you're showing velocities somewhere between, 0.2 and 1 meters per second. So somewhere between like, half and 3 feet per second. And I
Yeah.
wonder if you were to steepen that flume and have velocities that were maybe closer to 10 feet per second, if there would be more noticeable differences in some of the velocity, because I imagine there would be maybe higher turbulence in those cases. What are your thoughts on that?
I agree. It should be looked at. Yeah, I think that's a really good point. What it turns into, I'm actually really curious. Maybe we could speculate. Yeah, higher velocity. Um, l- I don't know. I'd have to think about that.
Yeah.
It'd probably take me longer to think about it than to just put together the model and run it and see what happens.
Yeah, I only bring it up because I think, again, the test that you presented definitely shows that if your velocities in your system are generally in a single direction downstream and are somewhere between 1 and 3 feet per second, I think it's safe to say that these results are pretty conclusive, at least in terms of the water surface impacts. I just would be curious if that's applicable at higher velocities. It'd
I
be an
think
interesting
that's yeah.
follow-on test. So.
I think that would be really interesting. I mean, we could dive into the equations, but we might put all of our listeners to sleep if we did that, and I might end up confusing myself more. So maybe what we'll do is do a on the next podcast, maybe have a brief follow up with the steeper flume. I like that idea, Ben. That would be really cool.
Yeah, yeah.
So let me end it with a couple more slides here. First of all, there are two different turbulence models available to us. One is called conservative and one's called non-conservative. The non-conservative is actually the original turbulence model that was added into RAS when 2D RAS first came out in version 5. Boy, has it been like 11 years already? I think it has. But then they added a new model called conservative, which, as the name implies, it conserves momentum better, okay, than the non-conservative one does. It's just the solution scheme that's used is a little bit more conservative. And so the manual will say, hey, just use conservative. That's the better one. The non-conservative is still in there so that you can have, your older models will still work and produce the same answer. But we recommend that you use conservative for any new models. That's what the manual says. I also look at it too in terms of near field or far field modeling. When you're doing near field, I think it's more important to conserve momentum than when you're doing more reach wide modeling. It's maybe not as important. You could probably get away with non-conservative and give you a similar answer to conservative. The other thing is conservative is, in my experience anyway, is harder to make work. It crashes more readily than the non-conservative one. And maybe that was you know, just me and maybe my particular models that I was trying to use it on. Maybe that's not technically the case everywhere, but I found conservative a little bit more difficult to use and take a little bit longer to run. Um, so in practice, I think non-conservative is going to be faster and easier to use and stable. Compares well to conservative for reach wide studies, but if you're doing a near field study, highly recommend you at least consider or try conservative. So let's get to the bottom line here because I think that's what people are interested in with turbulence. If you've got high Abbott numbers, remember your Abbott number is just your depth divided by your cell size. Okay, if you have high Abbott numbers, test turbulence. If you have significant velocity gradients, By that I mean change in gradients or change in velocity spatially. Test turbulence. If the water looks turbulent, test turbulence. If you have significant eddy patterns in areas of interest, and in particular, you're interested in those flow patterns, test turbulence. Calibrate if you can. If you've got data that you can use to calibrate, and this could be velocity measurements. Obviously, we saw that water surface, at least in the example I showed here, it's not very sensitive to turbulence, but certainly your velocity distribution and your eddy patterns are sensitive. So if you have that kind of data that you can use to calibrate, definitely do that. If not, and you do feel like turbulence should be used in your model, then do a sensitivity analysis on those coefficients. And whenever you do a sensitivity analysis, I always encourage people to understand what a conservative result is, because when you do a sensitivity analysis, you're looking at a range of realistic results, but you ultimately have to pick one to use, right? And the one you pick is going to be the one that gives you the most conservative results. So you have to know what that means for your modeling objectives. What is conservative? And remember, you've got those coefficients in the manuals, tables 5.1 and 5.2 of the HEC-RAS 2D Users Manual. And so use those to help guide you on what coefficients to use. And if you do use turbulence, try conservative. That's what the manual suggests. I suggest that if you're doing a reach-wide study, you're probably going to be just fine using non-conservative, but let's go with the manual. Try conservative. If you do have trouble with it, switch to non-conservative, especially if it's a reach-wide study. If near field, I think you really do want to try to make conservative work, so you might have to use smaller time steps to get it to work, maybe even adaptive time steps, or do some more work on your mesh to get it to work. So that's turbulence. I hope everyone feels better about what turbulence is in RAS and when they should be using it. But I think I'm probably going to use turbulence more in my models, Ben. I don't know. What do you think?
Yeah, I think it definitely doesn't hurt. Again, I'm kind of convinced just because of your point around the change in flow patterns. I'm typically focused on water surface elevations, especially with most of the work that we do. But I think your experiment, as well as just kind of thinking through it, certainly I think it's important to accurately account for the flow patterns and not just the water surface elevation. So maybe after in the next couple weeks, we can do some testing of that steeper slope flume and seeing if that makes a difference, because I'm curious at which ranges of velocity your conclusions are applicable to. But nonetheless, a very cool test, an interesting concept, and an important parameter to be aware of for anybody who does 2D HEC RAS modeling. I guess with that, we can wrap up for today. A reminder, if you're interested in learning more about HEC RAS 1D and 2D modeling, sign up for Chris and I's Fundamentals of HEC RAS 1D 2D class, which is going to start on October 1st of 2025. And certainly if you're interested in taking both that and the Advanced 2D class, there's a package that you can sign up for. It's about a 20% discount if you sign up for both classes. So consider doing that as well. And then also, if you are interested in coming and working with Chris and I on a daily basis in the consulting world, check out that H&H entry-level posting that just went up on Kleinschmidt Group's website. We'd be really excited to chat with you more in an interview setting and figure out if there's a good fit for you at Kleinschmidt. So, Chris, anything to add before we close out?
Well, one thing I gotta mention is the cool shirt you're wearing. If you come work for us, you're gonna get the Running Man shirt. So I wish I would have worn mine today, but I really like the black one too. The black one looks really cool with the Running Man logos on there. So nice choice.
Even if you don't come and work for Kleinschmidt, you can still get your own Running Man t-shirt by referring somebody who signs up for one of our HEC RAS classes. So if you've taken one of our classes before and you have a friend or a colleague who you think would enjoy one, have them sign up. You list you as a reference, and we will send you one of these along with a bunch of other cool full momentum solution swag. So it's not just for Kleinschmidt
Yeah.
employees, but certainly we'll give you access to a T-shirt if you join the team. So
Yeah, I think besides the t-shirt, the coolest one is the mug with the full momentum equation on there. And yeah, I use that all the time. I have it sitting on my desk. And whenever I'm interested in, what terms are in the turbulence part of the equation, I got it right there,
there you go.
right in front of
Perfect.
me.
Well, thanks again, Chris, for taking the time to discuss turbulence with everybody today. Thanks everybody for listening in. It's been a pleasure to complete episode 41 with you. It's been
Woo.
quite the journey, and enjoy your trip to Norway. And say hi to all of our RAS fans over there. So, with that, this has been Full Momentum Solutions, an HEC RAS podcast. Until next time, everybody. Thanks.